Hello and welcome back to the live stream. So, last couple of streams we implemented structs. We can set the members, read the members, and pass them around using as few copies as possible. What we haven't implemented so far is struct initialization. So you have to initialize each member separately, like so. If we do that syntax, this will not work. So let's just see what's going on. Okay, so we're hitting to do in the compiler and in Codegen. So let's just jump right in and process those. So compiler 297, unhandled non-scalar type. Okay, so we have the initializer for scalars, right? So scalar is like the basic types, like int and char and so on. So those are scalars. And when we initialize a scalar type, we can initialize them by expressions, or we can initialize them by a single initializer. That's fine. And then if you have an arrays, we allow multiple logic, so the full set of braced initializers, and something similar we need to allow for structs. So let's add a branch here if we have a struct. Which is, I believe, a decal type. Decal type of our type. Okay. So if it's a decal type, essentially we need to have one initializer for each struct member. So let's the decal type, so we get the decal and then we can get the struct. I believe it's called struct decal, right? So the struct, do I add node cast struct decal? Okay, so let's call you decal type. Okay. And then we need to recursively process the declaration. Similar, the initializer. So what we've been doing here as well. If it's the empty initializer, we don't need to check anything because it's fine. If you're having an expression initializer, that is simply not allowed. Yeah, we don't, so cannot initialize struct from expression. And if it's a braced initializer, we need to have one initializer for each member, at least. So let's call you member init, iterate over each initializer, and then we verify that this matches the corresponding member type. So we've got the struct members, which give us a range. Struct members begin. So the core member type. Okay. Okay. So then we process each type separately. Member decal. What are you complaining about? Oh, this is a double pointer. Okay. And then we process the core member. And if we already run out of members, so if .end, then we issue a diagnostic. Similar to this one right here. And then we log too many initializers for struct and break out of the loop. And then at the end, we need to set trailing initializers to the appropriate, so we didn't have enough. So if core member, we haven't reached the end of the members, then trailing members. We just increment u, trailing members, and we don't need this variable. Okay. And that should take care of the type checking for voiced initializers. Okay. Let me guess that bit. Why are we not? What's the issue here? Yeah, right. So we already reached the null pointer. Okay, something about this range stuff is consistently buggy. Oh, because we don't want the struct, we want the definition of the struct. Okay, that should do it. So the forward declaration of the struct, it doesn't have any members. Okay. So now we've reached that to do, and so we type check correctly. And if we do something like too many, then we get an error message. Okay. So now we need to handle the Codegen side. Codegen 1267. Unimplemented initializer for non-scalar type. Right. So again, similar logic. We need a special case struct. Decal type. And then get a struct. And then essentially we need to do the exact same thing right here. So if we're having an empty initializer, we need to essentially memset the entire struct object to 0. So we fill it with zeros, and the size is the aggregate layout. So auto struct layout, Codegen glove layout, decal type. And we want to fill that many bytes with 0. Expression in it is not possible. Struct cannot be initialized by expression. So we don't need to worry about those. Right, then we need to process braced initializer. What is that condition doing? So if you're doing constant evaluation, or if we don't evaluate the initializer at compile time, we need to manually initialize each array element. Right, otherwise, so we have a recursive thing here. So the braced initializer, this does, we want to get a single struct, like a constant, a global constant that contains the appropriate number of bytes, and then we mem copy that over. This case is easy. We simply need to mem copy the size. And here we've got a recursive call. And if we are inside the recursive call, then we need to initialize each one recursively. So what we want is we want to right, so we've got the address on top of the stack of the struct object, and then we want to initialize each member. And this can be done. So this does some pointer arithmetic, but this can be done easier. So we want to Okay. At this point, the top of the V stack is the address of the struct object. We want to initialize the current member of the struct. So for that, we first duplicate the address that's on top of the stack. Then we want to get the address of the member, aggregate member, which is member index member layouts.data member layouts.size, which can be computed here. We only need it here, so let's compute it here. Layout member layouts for member in members. We want to get the layout of that particular member. And then the member index starts out at 0 and increments at this point. Okay. And then for the trailing inits, same deal. So we want to essentially memset that many to 0. So which is the so how many bytes are those? So we want to get the offset of the current member that is left minus the entire struct. So current member offset log aggregate. Right, so that is the layout of the first members. So that way we get the offset. So we just look at the first couple of members. And then we want to essentially get the offset. So we want to start at the, I think let's do, since we're doing it at compile time anyway, let's do like a separate memsets for each members. That is just easier to do, I think. Yeah. So essentially we've got a separate loop. Trailing empty init plus I. And then the same deal. We want to memset the current member, so we get its address. And then we call memset for that particular thing. What's the, so you want destination byte count. So the byte is 0 and the count is member layouts member index dot size. So, and then we remove the base address of the struct, which is still left on top of the stack. I think that should be the appropriate logic. And here we don't want to initialize the element type, but the struct member. So get that particular struct member. And then get that type. Okay. So let's see what that does. It prints 11 and 42. Great. So what we're doing here is the mem copy of that data into the local struct object, and here's the data. So we've got the two members. This is the first one containing 11, and then this is the second one containing 42, which was set by this code right here. And if we do then like a trailing initializer, the last one will be set to 0. So that is really cool. Okay. Implement struct member struct initializer. Now there's a second syntax I'd like to support. So if you want to have like our function print foo, which takes our foo object and prints the members, then we want to say print foo. In C++, we can do 11 and 42, like so. But this is not legal C syntax. Right? Because like a braced initializer is not an expression in C. What would be legal C syntax is that. So we've got this is called a compound literal. It's a C99 feature as the error methods. And so we essentially need to specify the type of a compound literal. And currently we're not supporting that at all. Right. So it tends to pass something entirely different here. So this is a compound literal. And the grammar is we've got storage class specifiers that we're not going to worry about, a type name, and then a braced initializer. And this is essentially like the grammar. Then it has the usual, like the same constraints as the normal initializer, like this one that we just checked. And then it essentially creates an unnamed object of that type and passes that to the function. So yeah, let's do that. Compiler. So the grammar for an expression is right here. So we've got a bunch of, essentially it's like a cast. So we define right here. So essentially like we've passed a type name in parents and then a unary expression. So this is the grammar that we're already passing for cast operators. And then we want to pass it given a struct. Right, so this is almost the same grammar except for the storage class specifier, but instead of an expression, we're also having a braced initializer. Yeah. Let's I think it should be fine if we just do, instead of like an expression, we also support passing a braced initializer at this point. Okay, initializer, which is a curly bracketed. Yeah, right, we only want the curly bracketed list of initializers. So that one. Curly bracketed list of initializers, which we need to forward declare. Braced init. Is that. Want to pass the braced initializer or a simple expression. Yes. Then we need to adjust the thingamajig where we pass the casts, target type child, this one right here. We have a new case where we passing essentially a braced initializer, target type, and then we've got braced initializer. So the regular initializer, let's instead just reuse that logic. So let's say instead of passing the list here, we say that if we are having an open curly brace, then we are recursing and passing an initializer. And that means that the overload here now takes a target type and right here, this one, and an initializer, and returns an expression. Okay, so we need to define a suitable expression for a compound literal. So we've got a cast expression, a compound literal, compound expression is a basic node, which I then need to define. Cast expression, compound expression. Compound expression. Clove type, target type, clove init initializer. Yeah, good. So need to store you. And provide a getter for you. And let's make you construct like the other one. Okay. So that part's easy. That means that then the compiler, essentially we want to construct you and we want to do the type checking. So when we've got the init declarator right here, so we've got this function called verify init. We want to call you. Because we need the exact same logic. And then we are calling by init state position target type value. And then we're returning compound expression at the position, the target type, and with that value. Okay. Let's follow the compiler errors and see where we need to go from there. So we want to handle want to print you. And when we actually do print you, we want to dump your type, and then we want to do we print initializers somewhere? I don't know how we can print them. Let's see. Right. We don't handle them somewhere. I'm assuming during Codegen. Yes, during Codegen. So function call expression, cast expression. Need to handle you somehow. Compound expression. Let's do that later. Right. Let's just dump something here. Just so I can see the printing. So we've got a function call given by compound expression. I wanted to see whether we do support printing of compound literals. Yeah, so we just print them as a braced init. So can I then just say right, I'm guessing because they are implicitly visited by the tree. So can I just make you a child then? I don't think so. Or are they handled in the tree? Right, because they are wait, how are they printed? So I've got declaration. Where do we print the compound initializers? Because then, right, the decor. So we've got the variable decor. Right. Because they are containers of right. So they're just children of that node. I should just be able to make you a child. Because this is incomplete. Which is why that one doesn't work. Okay, but that means I can work with that. I just need to move you out of line. Let's move you here. Okay, now the printing code should work. So we've got, all right, I've commented you out. Right, so compound expression given by a standard. Okay, this is what I wanted to see. So let's do Codegen. Compound expression. So Codegen init. Right, we just need to create a temporary and then call Codegen init. That shouldn't be too hard. So create a temporary to store the object. Local. I can do something depending on the right, depending on the modes. If we can discard, it has no side effects. Because the expression needs to have constant initializers. So I will use the expression and result in an address. I don't think this is an L value. And compound literals. Semantics. Value type. Oh, no, it is an L value. Okay. So then in that case, we need to create an object. Here we already have an address. Okay. So we already have an address on top of the V stack already. And can just call Codegen init. Need to forward declare you. You can just call Codegen init. Context builder type expression initializer. Here, and then we want to result in the value. So here we need to create a temporary to store the struct into. And then build local builder Codegen the type, or rather the layout. When we get that address, do Codegen and leave the address on top of the stack. And essentially the same thing for that one as well, because the address is the value in that case. Constraints shall specify. Although it's not necessarily. So if we might need to load it, Codegen expression mode, value and type. Type is not null pointer. Then we can load you. Like so. And that worked. So that's cool. So we have created global that contains our initialization data. And then we create a temporary, get this address into it, and use that. And actually, so we create a temporary and then we copy the bytes over. But I'm pretty sure this is immutable. Is it immutable? I don't think. All right, it's not always immutable. So otherwise we could just reuse the global data that we're having anyway. But it is not necessarily immutable. Okay. So that's cool. Add compound literals. Okay. So let's add a couple of tests now that we are done with structs. Type def struct foo and a char b. So we want to make foo and return using a compound literal of 11 and a. Then we want a function that forwards foo and just returns you. Then we have a function that modify foo. Okay, we're missing one feature. Let's set u to 42 and let's set u to b. And then let's have a main that gets a foo, creates a foo object and okay, we're missing two features, and assigns it forward foo, make foo, at which point we want to, yeah, we have seal of asset is equal to 11 and f dot b is equal to a. Then we want to modify foo, at which point we are having 42 and b. Oh, I don't have capitals. Okay, so that's a basic test for structs. Okay, and now I realized I made two oversights that we're missing on tiny features before we can call it done. This one doesn't work. because we cannot initialize the struct from expression, which is of course wrong, because we can. I don't know why I thought this wasn't possible. So the verify init. When we have a struct that is an expression, we just need to, we cannot initialize an array because arrays can't be returned from functions, but we can do an expression. So we can do that. What are you? Ah, right. And then we should just need to handle Codegen. For struct expressions, this should simply be enough to right, that one. So we want to Codegen the expression and store it in the address that's on top of the stack. Okay, so now that part works. Initialize support initializing structs from expressions. And then the second feature is like to have that syntax, which simply wasn't handled by the parser at all. So this is postfix expression, this one. So postfix expression error identifier. And this is essentially an alias for the other one, where we first dereference and then we do the member access. So this should be quite easy to add. Just modify the parser. So we've got the member access. Given you, so I just need to differentiate between the two versions. Let's say enum member access period arrow period arrow, and then here we define the member access. Right here, so we got the object, and then we've got the tag postfix period. And then we need an overload. Why isn't that the... How do I use that? Oh, object given the postfix member access. Okay. Okay. So now, if right. So the object type, we might need to dereference here. So if op period, then return the type. Of the object. Okay, which isn't object, which is object or pointer. Okay. Otherwise, we need this needs to be a pointer. Dryad. Now try cast. Right, this needs to be a pointer. Constraints shall have pointer, right? Seal of pointer type, object of pointer, type, if it's a pointer, then we can just return pointer pointee type. Otherwise we have an error. So I cannot do member access pointer member access on non-pointer. And then we also want the object. So let's return in fact return the like so, statelet as create seal of a deref, unary op, how are they created. So we want to create a dereference operation. Deref. I guess I can just call you. So create unary state. What's the constructor for the object? It's a location and an enum. Object seal of unary op location seal of unary op deref, and then pointer. Not pointer, object or pointer. So we want to dereference you to get to the object. And not as kind. Okay. And then the object type is object type. Okay. And that might just work. Okay, so we messed something up. Oh, right. Because we're using object or pointer where we're supposed to be using object. Let's see. And that one works. Right, so it's just a quick and simple aliasing operation here. Okay. Okay, so that concludes structs. So we're now able to have like the essential features of structs that are necessary. We create them, pass them around, initialize them, and so on. So I think it's also a good point to stop the live stream now. We will continue on some other features in the future. So thanks for everybody who stopped by, and until then.